All right, now we're going to introduce an idea of stretches and compressions of linear functions. So part A, how does multiplying the output of a linear function affect its graph? Consider the graph f of x equals x plus 1. So this x right here is the input, but the whole thing, the x plus 1, is the output. If we plugged in an input to x, we would add 1, and that value would be the output. So g of x, what we're doing is we're multiplying the output, the x plus 1, times a 4. So how does that affect the graph? So let's take a look at what the original graph looks like, and then we'll take a look at what it looks like after multiplying the output by 4 and just compare. So we're going to do a table of values like we did in the last example. We'll go ahead and fill this in together quickly. All we're doing is f of x equals x plus 1. Our input is x, so let's input a -3 for the x. -3 plus 1 is -2. Now we're going to input a -2 for the x. -2 plus 1 is -1. And then if we just follow that on down, we're going to get a 0, 1, and 2. Now, what if we multiply the output by 4? Well, here's x plus 1. These are the outputs. So we're just going to take those values and multiply them by 4. So we're going to do 4 times -2. And our new output for our g function is -8. Then we're going to do 4 times -1. Because again, this x plus 1, we already figured out those output values, and now we're just multiplying them by a 4. So this is going to give us -4. Then we're going to do 4 times 0. 4 times 1 is 1, and 4 times 2 is +8. All right, so let's plot both of these graphs, these functions, and just compare to see what happens. So f of x, we have the point -3, -2. We have -2, -1. We have -1, 0, 0, 1, and 1, 2. We can see that looks like a linear function with a slope of 1. I'm going to label this as f of x. And I think our graph makes sense. Our function in slope-intercept form, the slope is 1, the y-intercept is 1, so we went up 1, and up 1 over 1, up 1 over 1, up 1 over 1. Okay, so now we're going to graph our second function, g of x. The input is the same, so our input is -3, but now our output got multiplied by 4, so we're going to go -3, -8, which actually is off the graph. We'll be able to get the next one though. Our input is -2, our output is -4, so that's the ordered pair, -2, -4, right there. When our input is -1, our output is a 0, so -1, 0. Our input is a 0, our output is a 1. Actually, did you guys catch my mistake on that? Maybe I should have kept writing it out. 4 times 1, that should be a 4. Well, it's a weird 4. 4 times 2. Okay. Oh man, glad I got that. All right, so when our input is a 0, our output is a 4. And then the next one just isn't going to fit on the graph. So here we have our g of x function. And what do we notice about how does g of x compare to f of x? One thing I notice is the slope changed. It got steeper. Up here we had a slope of 1, up 1 over 1, and we had this uphill line. Now our uphill line is much steeper. Our new slope is 1, 2, 3, 4 over 1, 1, 2, 3, 4. So our slope got multiplied by a 4. And then our y-intercept was at 1, and now our y-intercept is at 1, 2, 3, 4. So the y-intercept also got multiplied by a 4. So multiplying the output of a linear function by k scales its graph vertically. Oh, that's my marker. Here we go. All right, so that k value, when you scale a graph vertically, you could stretch it or you could compress it. A stretch is going to give you a steeper slope like this. a compression is going to give you a less steep slope. So it would have looked more like this possibly. And you can predict if it will be a stretch or a compression based off of the K value. If your K value is greater than 1, then you have a vertical stretch. It will give you a steeper slope. If the absolute value of K, so we always want to look at, the absolute value of K, positive, if that's between 0 and 1. So any fraction between 0 and 1, if it was a negative 1/2, we would have to consider a positive 1/2. If it's between 0 and 1, then it's a vertical compression. All right, so in that example, we just multiplied the output of a linear function by a constant k. So, oh, here it is. What if we multiply the input of a linear function by some value k? So we're going to use our same graph, f of x equals x plus 1. So let's just go ahead and fill in those table of values again. Although this time I just noticed our x's have changed a little bit. So we'll just quick do this. If we input a 0 for the x, 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. And then 6 plus 1, we jump to a 6, is 7. All right, so when you multiply the input of a linear function, what that's going to look like is the input is x, so the only thing we're multiplying by is the x. We're just going to take a 3 and multiply it by your x value. So now, if we have an input of 0, well, actually, yeah, our input of 0, so 3 times 0 plus 1 gives us 1. 3 times 1 is 3, plus 1 gives us 4. 3 times 2 is 6, plus 1 gives us 7. 3 times 3 is 9, plus 1 gives us 10. We're not going to be able to fit a lot of these on the graph. 3 times 6 is 18, plus 1 gives us 19. So let's graph both of these. We already know f of x equals x plus 1. So plus 1, I'm just going to graph this from slope-intercept form. Our slope is 1. Those ordered pairs are on this line right here. There's f of x. Now g of x, remember we're going to take the input from our x with our new output. So g of x, we have the point 0, 1. Then we have the point 1, 4. We have the point 2, 7. Well, I'm just going to go up 1 off. I know that's going to go up there. And then the rest of the points are off the graph. So I think we have enough points to draw this in. One thing we do notice, because it's linear, everything should fall in line in a straight line. So I can tell what the slope is here, up 3 over 1, up 3 over 1. So just to get a nice straight line, I'm going to continue that same slope and draw in our g of x function. So how do the two graphs compare? The slopes changed. This slope had a slope of 1. When we multiplied the input by 3, now our slope is 3. So we got a steeper line. The one thing that didn't change, though, was the y-intercept. The y-intercept of both functions is still at 1. So let's fill in our little questions here. Multiplying the input of a linear function f by k scales its graph horizontally. So that kind of makes sense. If you are going to multiply the input, which is your x's, by something, it will affect the x's. If you're going to multiply the output, the y's, it will affect the y's vertically. If k is greater than 1, the transformed graph is a horizontal compression. So our k was greater than 1. Our k value was a 3, by the way. That's what we multiplied everything by. This is considered a horizontal compression. So horizontally, it got compressed. So that made it look like it had a steeper slope. Kind of opposite of what we just saw. If the absolute value of k is between 0 and 1, the transformed graph would be a horizontal stretch. All right, so I know this video is long. We have, a couple quick questions. Now that we know how this works, let's just identify how these graphs compare. So f of x equals x minus 2. How does the graph of 0.25, all right, this little x right here, that's a typo. That shouldn't be there. So 0.25 times x minus 2 compare with the graph of f. So what we're doing is we're multiplying the output, because the output is the x minus 2, by 0.25. So when you multiply the output by something, that's going to affect the output, which is the y values. It's going to be a vertical. And then because our our k value was between 0 and 1, it's going to be a vertical compression. And we call that a scale factor. The scale factor is at 0.25. All right, part B, how does the graph of g of x equals 0.5x minus 2 compare with the graph of f? So this 0.5 is not being multiplied by the entire output. It's really only being multiplied by the input. So that is going to be, it's going to affect your input value. So that's going to be a horizontal. And let's see, we said, is it a compression or a stretch? If your k value is 0.5 is between 0 and 1, it's a horizontal stretch. And the scale factor for the horizontal stretch is 0.5.